Hey everyone, welcome back to the Bio365S discussions. This will be part one of a two-part video on renal physiology, and in this video I'll be talking mainly about the four main processes that occur in the nephron, those being filtration, reabsorption, secretion, and excretion. And then at the end I'll talk about how our kidney handles glucose, and from there we will go into part two where we do renal math. So I'll start out by just reviewing kind of the basic nephron and what is happening here. So we start this picture over here at the afferent arteriole. So the afferent arteriole is the blood vessel that enters the nephron, and it's the same kind of terminology that we talked about in terms of the endocrine system or even the nervous system. If it's an afferent arteriole, that means it is approaching the nephron. So we have blood coming into the glomerulus here from the afferent arteriole. So if this is 100% of blood entering into the glomerulus, not 100% of your blood at once, but if we think about the blood that is coming in from the afferent arteriole is 100%, then about 20% of that gets filtered in, and the other 80% exits through the efferent arteriole. So when this blood enters the glomerulus, this is a specialized capillary bed that I'll talk about in a minute, but it gets filtered out into the nephron. So you have fluid and some molecules, like maybe some ions, some organic molecules like glucose, and definitely some water that gets filtered in. So filtration is the process of moving from the blood to the lumen. And the lumen is just the inner tube, the inside of the tube of the nephron. So filtration occurs specifically in the glomerulus, and about 20% of the blood that came into the glomerulus will get filtered in. The other 80% will exit through the efferent arteriole. So let's look at this 80% of blood up here. Let's say that there's something in the blood that we don't want to keep in the blood, but it didn't get filtered in initially. If there's something in the blood that didn't get filtered in and we don't want to keep it, then we can secrete it. So secretion is moving also from the blood to the lumen, but secretion is happening in the peritubular capillaries. So even though it's the same direction as filtration, it has a different name because this is occurring in a different spot along the nephron and in the blood vessel. So this 20% of blood that is in here, a lot of this stuff that gets filtered in, we actually want to take it back into our body. So if there's something in the nephron that we don't want to excrete, that we don't want to get rid of, then we will reabsorb it. So reabsorption is moving from the lumen back to the blood. So it's going back to our body because we want to hold on to it. So anything left over in this tube that makes it all the way down, it will get to the collecting duct where it will be excreted. So excretion is urine production, and it is moving it from your nephron to the outside world, to the external environment. So excretion is different from secretion, and you need to know the differences between the two because it's really important when we say something is secreted, that is different from saying something is excreted. And I'll go into that a little bit more in the next video. But those are the four basic renal processes that are happening. So I want to talk about filtration a little bit more, and specifically the filtration barrier. So when we zoom into the wall of the glomerulus, we see this picture. And the filtration barrier has three different layers to create the filtration barrier. So the first layer is just the capillary endothelium. The glomerulus is a capillary bed, and like all other capillaries, it is the single layer of endothelial tissue, but this one is a little bit specialized. It has slightly larger pores in the endothelium, and these pores, they are a barrier for size. So the capillary endothelium is a size barrier. So things that are small enough to fit through those pores will fit through. But if something is too big and it doesn't fit through those pores, then it will not be filtered. So it will be selectively not filtered. So filtration is selective in the sense that it excludes size. The second layer is the basal lamina, or the basement membrane. And within our plasma, we have a lot of plasma proteins. And those proteins have a negative charge on it. So in the basement membrane, what we have made is a barrier that also has a negative charge on it. So inside the basal lamina, there's a negative charge. So if any plasma proteins are able to get past the endothelium, they will encounter this negatively charged basal lamina. And we know that like charges don't like to be next to each other, so they will repel any plasma proteins. So the basement membrane is an electronic barrier because it excludes anything with a negative charge, such as your plasma proteins. All right, and then the last one are the podocytes. The podocytes are these purple teeth-looking things, and they are another size barrier. So similar to the capillary endothelium, it has these pores in between. Anything small enough to fit through them will fit through. So we see that while filtration is non-selective, that's kind of a relative term. It is selective in the sense that it excludes molecules that may be too big, or it will exclude proteins with a negative charge. So it is selective in the sense that it can only filter in things that are small and positively charged. Things like your plasma proteins don't get filtered in. Things like your red blood cells also do not get filtered in. Red blood cells are too large. We usually don't see red blood cells appear in our urine. If you do, then that is a sign of some sort of physical damage to this filtration barrier. All right, so the next thing I want to talk about for filtration is the driving force of it. So when we have the blood coming into the afferent arteriole, so this blood that is moving throughout these capillaries, that blood exerts a pressure on the walls of this blood vessel. That pressure is called hydrostatic pressure, P sub H. So that hydrostatic pressure will cause this blood to be physically squeezed out into the Bowman's capsule and into the lumen of the nephron. So we get all this fluid now out here. So if there's fluid on the outside of the glomerulus, well, that fluid is going to exert its own force back on the walls of the glomerulus. So this pressure coming from the fluid is similar to hydrostatic pressure because it's acting on the walls of the capillary, but it's coming from outside the glomerulus, so it's resisting filtration. So that is one of the resistant forces to filtration. The other is osmolarity. So we have osmotic pressure resisting filtration. So if we think about the blood in here, if you are squeezing out water into the glomerulus, well, what you're doing is you're increasing the osmolarity in the glomerulus because you're squeezing out water and holding on to solutes. And then at the same time, if you're squeezing out mostly water, the osmolarity of the nephron is going to decrease. Well, we know based on osmolarity and tonicity that water will always move from an area of low osmolarity to high because water's job is to always go and dilute the more concentrated area. So the osmotic pressure is another resistant force to filtration. However, your blood pressure is usually higher than both of those, so you get a net filtration pressure, which is the driving force of filtration. So your blood pressure is the driving force of filtration. If you have a drop in blood pressure, you will filter less blood into the kidney because you will be decreasing this hydrostatic pressure in the glomerulus. So that's the driving force of filtration. All right, so going back to this picture, when we look at filtration, if you were to look at the total amount of blood that you filter into your kidneys every day, that is called your GFR, your glomerular filtration rate. So it's the total amount of blood you filter in per day. And your GFR is very tightly regulated by your body. And the site of GFR regulation is the afferent arteriole. So I wanted to go over the two local control mechanisms to regulate or to auto-regulate the GFR via the afferent arteriole. And the first one I have is myogenic response. So the myogenic response, it's occurring in the afferent arteriole, and it is happening in response to a high blood pressure. So if you have a spike in blood pressure, what will happen is, if this is our afferent arteriole, so if you have increased blood pressure through this tube, well, that blood is going to exert a pressure on the walls of that vessel. And when it exerts that pressure, that vessel will expand. So you will get expansion. It will be physically stretched more by the increased pressure. Well, when this vessel gets physically stretched more, in the walls of these vessels, we have mechanogated calcium channels. So when it gets physically stretched by the blood pressure, mechanogated calcium channels open up and we get an influx of calcium to the smooth muscle of that arteriole. And if it's going to the smooth muscle, well, we know what calcium's role is with muscle. We know that calcium will enter the muscle and bind to the troponin-tropomyosin complex to remove it from actin, which will reveal myosin's binding sites so that the cross-bridge cycle can occur, which is a muscle contraction. So when calcium enters, you get a muscle contraction. So then the result is you get a narrowed blood vessel. You get vasoconstriction in that blood vessel. So it started normal, and then it stretched, and then it vasoconstricted. So what effect this has on GFR? We know that vasoconstriction increases the resistance through the afferent arteriole. Increasing resistance through a blood vessel will decrease blood flow, which will decrease GFR. So if you started with a high blood pressure, that is also starting with a high GFR. So then the end result is the lower GFR. This is an auto-regulation of GFR. So this is the myogenic response. Genic meaning origin, myo meaning muscle, because this response originates in the smooth muscle of the afferent arteriole. And this is an intrinsic property of the afferent arteriole to self-regulate the blood flow through the nephron. So that's one of the ways we regulate GFR. The other way we regulate it is tubulo-glomerular feedback. And between the two local control mechanisms, this one has the larger role in regulating GFR rather than the myogenic response. So tubulo-glomerular feedback has a stronger role. So just like last time, this starts with a high GFR. So maybe something that increases your blood pressure will increase GFR. So if you have an increased GFR, you are going to be filtering more fluid into the nephron. So the fluid that's going in here, when we look at the anatomy of this, we notice that the proximal tubule has this descending loop and ascending loop. And when it ascends, it goes back towards the afferent arteriole. So when the tube of the nephron is physically stretched more by the increased filtration, by the increased water or volume inside of the tube, these cells, the macula densa cells, sense that stretch. And when the macula densa cells sense the stretch, they send a paracrine signal to the neighboring granular cells. And the granular cells are on the afferent arteriole. They will tell the afferent arteriole to vasoconstrict, because vasoconstriction increases resistance, which decreases blood flow, therefore decreasing GFR. So the whole goal is to get GFR back down, because we started with an increased GFR. So this is negative feedback. If we started with something too high, the end response should be to get that parameter lower. All right, so this is the communication, the local communication between the tube of the nephron and the smooth muscle of the afferent arteriole. That's tubuloglomerular feedback. So if we look at the name of this, it is the tube of the nephron going to the blood vessel, which is the afferent arteriole, to regulate the blood flow through the glomerulus. And this is feedback because it works via a negative feedback mechanism. All right, so that is everything I had to say on GFR. The next thing I wanted to talk about was glucose handling in the kidney. So to do this, we are going to need that's not it. We're going to need an axis. So go ahead and draw yourself an axis. And this graph is going to be glucose handling. So on the x-axis, we are going to have plasma glucose concentration. And on the y-axis, we are going to have transport rate. All right, so when I say handling, I mean, how does the kidney deal with glucose? Does it fully reabsorb glucose? Does it secrete glucose? What is the net process that happens in the kidney for glucose? So the first line that we are going to do is going to be a nice linear line through the middle. This line represents the filtration rate of glucose. So I'm not going to put values on the x and y axis for this, but if we interpret this line, then what this line is saying is, as you increase the amount of glucose in your blood, so moving to the right on the x-axis, you will filter in more glucose into your kidney, which makes sense. The more glucose in your blood, the more glucose that enters your kidney. That's what this is saying. All right, so we are going to draw another line, and I'm going to change colors because it's going to be right on top of the filtration line, and I'll make it dashed so you can still see it. So it is going to be right on top of filtration to a certain point, and then it will plateau. So this blue dashed line is the reabsorption rate of glucose. All right, so to interpret this line, we need to look at it at two different times. First, we should look at it from the beginning to the plateau. So that first section of this line, the way we interpret that is saying, okay, the more glucose that we are putting into our blood, we are able to reabsorb all of it, because it's a 1-to-1 ratio with filtration and reabsorption. They are equal to each other. So every bit of glucose that is filtered in, it will get reabsorbed. That's how you interpret the beginning of this. But starting at this point, starting at the plateau, so the plateau here, the way we interpret this is, even if you put in more glucose into your blood, your reabsorption rate has reached its maximum. So you are reabsorbing glucose at the maximum rate despite the plasma glucose concentration increasing. So even if you add glucose to your blood, you will not reabsorb glucose any faster than what you are currently doing. All right, so some other important things to label on this is if we were to trace this out to the y-axis, this point on the y-axis is Tmax, transport maximum. And that is just the maximum transport rate for glucose reabsorption. And if we were to trace this point down to the x-axis, this point on the x-axis is the renal threshold. And renal threshold is the plasma concentration, because this is an x value. Renal threshold is the plasma concentration at which Tmax occurs. All right, so to put this into a little more perspective and context, let's look at the actual mechanism on how we reabsorb glucose from our kidney. So what we're looking at here is an epithelial cell. We have ECF on the right, and we have the lumen of the kidney on the left. So the goal is to get glucose from the lumen all the way to the ECF. So if we look at this, on the luminal side, we have glucose and sodium moving through the sodium-glucose cotransporter. And on the basolateral side, we have glucose moving through the GLUT carrier. So the glucose carrier and the sodium-glucose cotransporter are both carriers. And we know that carriers have a specific binding site for their molecules so that they can be saturated. So if they have a specific binding site, that means they can eventually become saturated. Meaning if you keep adding glucose to this side, you will eventually reach a maximum rate at which glucose can cross this membrane. No matter how much more glucose you put out here, you will reabsorb glucose at the same rate because that transporter has become fully saturated. So because glucose reabsorption is dependent on carriers, then glucose reabsorption can reach a transport maximum. That is what is happening on this graph. Here on the plateau, our reabsorption rate of glucose has reached transport maximum because those glucose carriers have been saturated. So that is what is happening. And one more part to this graph. Starting at the renal threshold, we see another line. And this line represents excretion rate of glucose. Okay, so what this green line is saying is once you have reached your renal threshold or past your renal threshold, the more glucose you put into your blood, the more glucose you will see in your urine. So this is urine because it is excretion. And we don't see excretion occur until the renal threshold has been passed. Because before the renal threshold, on this side of the graph, every bit of glucose that we filtered in, we reabsorbed. But now, once you pass the renal threshold, even though we're filtering in more glucose, we are not reabsorbing all of it. We have reached this transport maximum for glucose. All right, so hopefully that made sense. Another example, kind of unrelated to physiology, to put this into perspective, is from a show that maybe some of you watched when you were little, called Drake and Josh. So if you watched Drake and Josh growing up, then you will appreciate this next example. If you didn't, it's okay. You will hopefully still understand the example. Okay, but there's an episode of Drake and Josh where they get a job at a sushi bar, and they're told that their job is to sit behind a conveyor belt and pack all of the sushi that comes across the conveyor belt into boxes. So when they start, the sushi is coming down the conveyor belt pretty slowly. So they're like, oh, this is really easy, like it's coming down slowly, there's not a lot of sushi. every bit of sushi that passes them, they are able to box. But eventually, so much sushi starts moving down the conveyor belt that they can't possibly grab it all. So then it gets really dramatic. They start trying to eat all of the sushi. They start throwing it against the wall. One of them starts laying on the conveyor belt to try to just stop it from moving. But let's say that one piece of sushi got past them to the other side of the wall. Once one piece of sushi got past them, that didn't mean that Drake and Josh stopped moving the sushi. It actually meant that Drake and Josh were moving sushi at their maximum rate and that they couldn't possibly get the sushi off the conveyor belt any faster. And that is the same thing that's happening with your kidneys. Once you see glucose appear in your urine, that doesn't mean your kidneys stopped reabsorbing glucose. That actually means that your kidneys are reabsorbing glucose as fast as they possibly can, but there's just too much glucose that they can't possibly do it. So just like how Drake and Josh, had two hands and one mouth to grab the sushi, your kidney has a limited binding site in those two glucose carriers. So hopefully that helps you understand what is going on with glucose handling in your kidney. I do have a confession that I actually did not watch Drake and Josh growing up. And maybe some of you are like gasping and losing respect for me as soon as I say that. But I did watch this episode so that I can explain the scene to you. For some reason, I didn't watch Nickelodeon growing up. I was like exclusively Cartoon Network and Disney Channel. So I don't know how Nickelodeon didn't make its way in there. But I know that episode and I know how it relates to your kidneys. So I hope you appreciated that. Hopefully it made more sense. Starting from this graph, we are going to move into renal math. So I will see y'all in the next video.